Hello, everyone. This is my ICCAD 2024 presentation on Balor, a HLS source code evaluator. Design space exploration for high-level synthesis. High-level synthesis allows us to generate circuits directly from high-level languages, primarily for use on FPGAs. And although it raises the level of abstraction, it does not free us from many of the hardware decisions that must be made. You can see some example topics here. To achieve high-quality circuits, these decisions must be made well, and then encoded directly into the source code file itself. We call this decision-making process design space exploration. We start with naive code and transform it entirely using our hardware expertise. For a high-quality design, the output code is often completely unrecognizable. You can see an example here of how much longer it is. Design space exploration takes place in a loop like this. Crucially, it requires some way to evaluate candidate designs, to check their performance, but also resource utilization. Do they fit on a specific target FPGA? The gold standard for this is to actually implement the circuit, to perform HLS all the way down to place and route, and consider the actual circuit produced. But with implementation taking hours, if not days, and thousands or tens of thousands of candidate designs, this is simply too computationally expensive. We therefore need some way to estimate the crucial circuit characteristics: latency, clock period, resource usage. We also need to estimate these without performing HLS. This means to perform the estimation directly from the source code. This long-term research goal of rapid, accurate evaluation is something actively worked on in this research community, and is the goal this work seeks to contribute towards. In this presentation, I'm introducing Balor, an open-source, GNN-based HLS source code evaluator. In the first stage of the ML contest for chip design with HLS, I achieved first place with an approach based on Balor. They asked us to minimize this metric, which includes both regression and classification, and so you can see the gap between our results and other competitors. For those who have never seen these estimators before and want to know the rough magnitude of the error, on the open source benchmark database for HLS, we achieve 4% error on LUTs and 6% on latency. So why graph neural networks? Why are graph neural networks the state of the art? It's because they encode topological information. If we consider the graph on the left, the GNN encoder produces an output vector containing the same information. In the context of this specific problem, the kernel code is given to a graph compiler, which builds a graph representation. The GNN encoder produces an embedding, and then a traditional deep learning estimator produces the actual quality of results estimates. So why does Balor improve over previous works? What is the origin of the contributions? Well, previous works used an existing software-oriented graph compiler. And in contrast, Balor has a completely new HLS-tailored graph compiler. The changes we made allow us to mitigate issues inherent to this estimation process at the earliest stage, and therefore open up opportunities for further improvements throughout the entire estimation stack. Previously, crucial cross-graph interactions, where two nodes on far sides of the graph influence each other for the estimation process, forced the use of large receptive fields. What is a receptive field? It's a mathematical window into the graph. Like all mathematical windows, it's centered on a certain point. If we say, for example, this yellow node. With radius 1, nodes one edge away are included in the receptive field. As the radius grows, more and more nodes are included. The first issue is that GNNs have poor scaling behavior. Large receptive fields cause redundant processing, which reduces estimation accuracy. The second problem is that the field is not even. Nearby nodes, their information arrives early in the estimation process and has a high impact. But the further away a node is, the later its information arrives, and the less calculations that information is used in, limiting the impact. If we compare them directly, why GNNs have redundant calculations and limited cross-graph interactions? Local GNNs can have increased accuracy, but have no cross-graph interactions at all. Local GNNs have another problem. Since their small receptive field sees only a small subgraph at a time, they need that subgraph to be information-rich. They therefore need the graph as a whole to be information-dense. This leads us to 3 questions for how can we improve graph neural network quality of results estimation? Can we improve the graph? Is it HLS specific, and is it information dense? Can we move to a local focused GNN? Can we localize these problematic cross-graph interactions? And if so, how should we change the GNN architecture to reduce the receptive field size? Finally, can we use hierarchical approaches? I'll explain exactly what these are when we get to them, but the crucial issue is we need some way to reduce the graph size. So let's look at the first question. Programmable is the name of the software-oriented graph compiler used in previous works, and it builds the graph from the LLVM IR. With an example kernel, the output graph looks like this, and in contrast, Balor's graph compiler produces this graph. On average, our graphs are 1/3 the size, and so have 3 times the information density. How do we build this graph? Well, we first put each line of code in program order, adding branch nodes anywhere there is divergent control flow. But a line of code corresponds to many things happening on the hardware level, so this is not the graph we use. We break it down further into indivisible hardware actions, and this forms the basis of our graph. Next, we label data type information onto the existing hardware action nodes. We add a node for each variable declaration and connect it directly to all reads and writes of that variable. Finally, we add data flow edges, and this forms our final graph representation. In terms of concrete differences, Balor is tailored to the HLS process, does not include inapplicable information related to pointers, function arguments, and struct indexing. It also includes previously omitted hardware information. Balor uniquely encodes both variable declaration type and common math function identities, as both of these can strongly affect resource usage. We also simplify the graph by placing data type information inside the existing nodes. This alone doubles the information density. I'm going to show you evaluation results at several points in this presentation, but I'm going to show you the setup now. For the architecture, we're using GNN DSC. It's not the most recent state of the art, but more recent works add additional features around the GNN core, and so any improvements are both foundational and transferable. The dataset is the database for HLS. We have more than 36,000 data points synthesized with Vitis HLS from 29 mock suite kernels. And a data point is one of these 29 kernels with a specific combination of HLS pragmas. We're looking to estimate latency, clock period, and resource usage. And the error metric we're using is percentage error. If I show an example scatter plot here, you can see the distribution of the predictions. The x-axis is real flip-flop usage, and the y-axis is the estimate. For a perfect estimator, every point would be on the yellow line. Since we want to compress this to a single number for comparison, we take the mean. So this is a bar chart of that error as relative error. We want error to be 0, so we want the bars to be as low as possible. It's relative error. So if the bar touches the line for 1 at the top, it has the same error as GNN DSC. And you can see when we use Balor's graph compiler, we get a reduction in error across the board. This bar chart shows the number of multiplications required for inference. Since our graphs are 1/3 the size, we use 1/3 the number of multiplications, showing we have reduced the redundant processing and therefore the computational cost. And in conclusion, information dense, HLS tailored graphs reduce both error and cost. Next, can we move to a local focused GNN? Well, our smaller graphs have already localized a lot of interactions since the nodes are closer together, but we have one remaining one, HLS pragmas. Here we have a Vitis HLS pipeline pragma. Previous works added this pragma as a node to the graph, a philosophy we call information has location. We place the information at a single place. But this isolates the pragma information. A GNN with a large receptive field can still propagate this information, but as we saw, this limits its impact. Our philosophy is locations have information. If you know that a node is pipelined, you can directly label it as such. In this way, we distribute the information to all relevant nodes. This is as local as you can get. The information is present at the very beginning of inference, and therefore we maximize its impact. Now that we have localized the interactions, how should we alter the GNN architecture? This is the architecture for GNN DSC. If you don't look at GNN architectures very often, the details aren't super important. But what does matter for a move to a local focus is that we reduce the number of message passing layers from 6 to 2. And this reduces the receptive field size to 1/3 of what it was previously. With both points complete, we can look at the evaluation. Error again falls across the board, LUTs to 0.57 and latency to 0.73. The number of multiplications also falls, as reducing the receptive field size reduces redundant processing. And we can see local focused approaches further reduce both error and computational costs. Let's look at hierarchical approaches. Well, what are hierarchical approaches? Flat GNNs go from graph to vector in a single step. And in contrast, hierarchical GNNs go from a large graph to a small graph to a vector. Reducing the graph size doesn't lose any information, and so we benefit from increased information density. But in order to do this, we need some way of clustering the original graph. If we look at our running example, how should we cluster it? Well, good clusters already exist, basic blocks in the control flow graph. If you haven't seen basic blocks in a while, they're regions of code with no control flow, either convergent or divergent. If I color in the running example, you can see there are 4 basic blocks, and the control flow graph looks like this. In order to get from many nodes on the left graph to fewer on the right, we aggregate each cluster and can then do even more graph learning on the control flow graph. In terms of architecture, we keep the action level GNN the exact same, but add additional processing on the basic block level. Importantly, this is trained end to end, so we don't have to worry about separate convergences, and it doesn't require any additional data. For evaluation, error drops further, LUTs to 0.49 and latency to 0.70. Computational cost rises only slightly, as hierarchical approaches are very cheap. And the conclusion is therefore hierarchical GNNs reduce error at low cost. If we step away from individual metrics, our overall error is 0.61 of the baseline, and our cost is 0.18. In conclusion, Balor uses information-dense, HLS-tailored graphs, a local-focused approach, and hierarchical GNNs to increase estimation accuracy and strongly reduce computational cost. Thank you very much.